All right, so it's my pleasure to be here and talk about deep learning with you guys. So we're going to talk about deep learning on business data at Uber, and emphasis on business data because we also have a lot of, let's say, self-driving data that is slightly different. So let's start with why do you want to do deep learning in the first place? This is famous chart by Andrew Ng, where he shows that traditional machine learning algorithms, as you reach certain scale of data, get saturated and they stop adding more value, whereas deep learning algorithms continue to improve. And as it becomes cheaper to collect and store the data, more and more companies have huge amount of data that could benefit from building models using deep learning. Deep learning nowadays is state of the art for many domains, such as images, text, speech. And so that allows us to capitalize on massive amount of research that is currently happening in the community. Additionally, deep learning is not sort of black and white distinction from traditional machine learning models. So you can combine deep learning models with machine learning models. And for example, you can build deep learning model that will be connected to, let's say, XGBoost model. And that together could be your solution for your machine learning problem. So at Uber, we use deep learning for many domains. As I mentioned, there is autonomous cars, but there is also a lot of business use cases. So we do Uber Eats, we predict ETAs, we use deep learning for customer support, dispatch, and many, many other areas. So for us, we have, because we have a lot of data for most of these problems, deep learning makes a lot of sense. So how does it work? So deep learning is sort of called deep learning because models that it uses typically have many processing steps called layers. And so typically what you have in the front, you have some input data that you feed in, you do some processing on it, and then you do these nonlinear transformations. It's not just a sequence, so it could have forks, it could have recurrence, it could have many things. And the way you do training of these models for supervised use case where you know the ground truth is you feed both input data and you feed labels. You compute a prediction, you compute delta between your label and prediction, and you backpropagate the errors. So that's cool. It talks about training, but as many people talked today before, this is actually a very small piece of the whole puzzle. And so if we zoom out a little bit, we actually see a lot more components. So we can see that before you actually do the training, you need to have features, you need to have data, and so you need to have feature store. After you did your training, most likely you want to use your model to do predictions, and you can have batch and real-time predictions. So we can see here that not only deep learning, not only training is sort of small piece of the puzzle, but also there is multiple dimensions. So there is data preprocessing, there is feature stores, there is deployment, and finally there is real-time and offline version of both. So for example, when you're doing, let's say you're a service company that has online services, you will likely need online version of your model for many things. But at the same time, if you're doing advertising, maybe you don't need real-time information of who to send new announcements to. So you oftentimes have both real-time and batch use cases. But if we zoom out even further, we see that this instance of pipeline is typically gets replicated for different use cases. And you don't want to build it out from scratch. So normally you have a system which allows you to create such pipelines really easily. You need to have management interface. You need to have authoring interface, so where you can create your models. And you finally need to have monitoring. So how can you do this? Today there is a lot of options. There is a new option called TFX, which is very nice. And there is also Spark. Spark has been around for quite a while. So at Uber, we actually chose Spark. And the reason we chose Spark is it's very good for ETL. It integrates with traditional ML algorithms like XGBoost really natively. There is existing machine learning systems at Uber built on top of Spark. And finally, because of all these things, we have very close collaboration with Spark community. So let's now go back into that overall architecture that we saw before and see how we can implement all of these things with Spark. So feature store, that's probably not going to be surprising that you can do feature store in Spark. So for feature store, there is batch and real-time components. So batch, very easily you can do ETL using Spark. For real-time components, you can use things like Flink, you can use Cassandra, but all those things integrate very nicely with this like Apache Hadoop Spark ecosystem. So overall, I don't think many people will be surprised if they see Spark as an engine for feature store. The second part is training. Now that's a little more interesting. So training, before we saw that we have this deep learning pipeline that is typically TensorFlow, PyTorch, and now you need to run it in Spark. That's something that not many people do. So how can we do that? There is few things. And there is few things that actually shows that it's a very good idea, at least for us. One thing is preprocessing. So sometimes you need to do something with your input data before you feed it into your deep learning pipeline. One example is, let's say you want to do one-hot encoding, or maybe you want to do string indexing, where you map your words to different numbers. And maybe beforehand, you actually don't know how many numbers or categories you have. So before you create your model, you actually need to do analysis of data in some automatic way and collect statistics about data. And after you do that, then you train your deep learning model that may actually use some of the parameters of your initial step to tweak it a little bit. Let's say if you're determining how many different words you have, that may affect size of your embedding table in your model. So in Spark, this actually can be solved pretty naturally using the SparkML pipelines. So SparkML pipelines have concepts of estimator and transformer and pipeline, and the difference is pipeline you can think of as sequence of estimators, and estimator can be trained, and when it's trained, it becomes transformer. So what it means is what we can do is we can sequence our pipeline in a way that all our preprocessing is done as a sequence of estimators, which can be trained, and so they can determine these embedding spaces, these mappings. And then when we train the actual model, we will already have information from the previous steps. So for distributed training, we use code, and the reason we do that is what we find is as you deep learning requires a lot of data makes things very slow, and so you actually need to use a lot of compute resources to train your models in a reasonable time frame. So we also found that most of the models actually fit in a single server, so that we could basically do data parallel training. We have replication of the models on multiple compute devices, be it GPUs or just separate servers, and then we train them in this data parallel way. And that's where Horvath really works very well. But there is still a slight disconnect. So you have TensorFlow, and you have your data in Spark. So you have it in data frame, but now you need to ingest in TensorFlow. It's not trivial how to do that. And the solution that we came up with is called Petastorm. It's actually open source. What it does is you would take your data frame in Spark, and you would save it as Parquet file. And the good thing about Parquet files is that it actually solves a lot of problems for you. So when you do deep learning training, you need to be able to stream data from HDFS, as your data size is pretty large. You need to be able to shuffle, so you basically need to be able to read data randomly or semi-randomly, and you need to be able to, in some cases, maybe you're saving. What you could do is you could just read some of the columns that you wanted instead of all of them. And Parquet allows to do all these things, and Petastorm is basically a library that connects TensorFlow to read those Parquet files. So end-to-end architecture looks like this. You basically have data in your data lake, for example, Hive. You do Spark, you do data preprocessing and save the data in HDFS. And then use Petastorm and Horvath to spin up a lot of training workers, which would, in parallel, read the data in a random way. So that covers the training part. Now let's talk about prediction. So I was saying that we use SparkML. SparkML is Java. And deep learning is C++. So, and we need to run them together. Interesting. We also would like to allow our users to bring their own version of the framework. So as some of the speaker mentioned before, some people want to use TensorFlow 2.0. Some people want to use TensorFlow 1.11. Some people want to use TensorFlow with their Git SHA that has their patch that somebody pushed just for them. And we don't want to support all these combinations ourselves as a sequence of pre-baked images. So we actually allow people to kind of customize their image. And we basically have two containers that run together. One container has our Java part that runs SparkML, and another container runs deep learning. And so this architecture kind of shows how this fits together. So now let's talk about authoring. Data scientists love Jupyter notebooks, and we want to support being able to define these models in Jupyter notebooks. So how can we actually do that? How can we do all these steps in Jupyter Notebook? So I'm going to show our way of doing it and our APIs that we came up with. So the way it works is this API shows data access. So if you've seen Spark SQL before, this should be very familiar. One thing we do after we extract sort of basis information, we do join with feature store, which should be very familiar from a couple of talks before. So we basically specify which features you want, and they get joined automatically in Spark. Then we do data prep. So data prep is this stage where we do all these one-hot encoding, string indexing, and other kind of lookup transformations. And then we can split our data frame into training and validation. And now we do model construction. And so model construction, you basically can use Keras, or you can use TensorFlow, or you can use PyTorch. You can construct model within the same notebook. And that's actually very nice because a lot of people make mistakes when they construct models, this guy especially. And so it's very good to be able to see errors right away without having to spin up some new container or spin up new job before you actually see the error. And then you can train a model. So the way we train a model, we have this estimators that you can pass this model into, and then we can fit them. And so these estimators actually have exactly the same API as all other Spark ML estimators, which allow you to chain them together with the rest of your Spark ML pipeline. So here we train this estimator with some hyperparameters that we can pass. And then after it's fitted, you get transformer, which is a model that you can transform and basically do predictions. So that's very nice for doing evaluation and making sure that your model quality is good. And then if you want to do, let's say, hyperparameter search, you can have a loop around that. And finally, we can deploy a model. So what we do, we take the model, we convert it into servable model, because we need to build container for that model. And then we create sort of end-to-end pipeline, which will have transformation, it will have our model, and potentially it will have some post-processing steps. And then we upload the model and deploy it. So what we see here is basically we have APIs that cover end-to-end creation of the models, all within the same notebook. And you can also run those interactively if you do it on sample data. So you could basically step through your model creation and make sure that everything works fine. And then once you see that it's working fine, then you can scale up amount of data and run kind of batch experiment, and then maybe do some hyperparameter tuning to see which combination of hyperparameters gets you best results. Now, other problem is, what if you don't know deep learning? So before I shown you the kind of model that you could create with Keras, if you know how to use Keras, but maybe you don't. So maybe you starting more from like traditional machine learning background, you know how to get the data, but you don't know much about deep learning. For that, we create Ludwig. So Ludwig is our library that allows you to do deep learning without writing code at all. So with Ludwig, you can just define your model as YAML file. You can download data on your laptop or on your server with GPUs and run a training. And then you can deploy that model as kind of Ludwig package in your application. It does support a lot of use cases out of the box. It does support NLP use cases and many others. And it has a lot of very good documentation. So far, it's mostly focused on using a single kind of data source that fits on your disk. But we're working on Spark support as well. And so to recap, I was showing you that companies benefit from deep learning if they have very large data sets. I've shown you architecture of Uber deep learning system and how we use notebook-friendly APIs to define end-to-end pipelines. I've shown you that Spark, Horowitz, Petastorm form open source foundation for a potential deep learning platform that you may want to build. And I've shown Uber Ludwig open source software that allows you to do deep learning without writing code. I think I have some time, so I can show you Ludwig examples. So basically, you can see here one of the simple models that you can define with Ludwig. It's basically a YAML file like this. And that's actually going to do word embedding CNN that will classify your text. So in order to do that, you just need to create this YAML file. And then you pass it data. And that will train your model. So with Ludwig, there is a lot of these kind of common use cases that you can solve with writing very little configuration file. So that's something potentially to look at. And finally, there is link to other sort of blog posts and materials that you may find interesting. And I can answer some questions.
So you didn't mention the word Kubeflow in your whole talk. Could you speak a little bit about why?
This was built before Kubeflow was around. And so we didn't take Kubeflow. As I mentioned, TFX and like this Kubeflow TFX ecosystem is alternative option, but this is not the option that we chose.
Okay. So is there a plan in the near future or long-term future to ever have anything like Kubeflow inside Uber?
Not at this point. We're basically pursuing, at this point, we're pursuing Spark approach, where we define pipelines either in Spark or in workflow engine that we have internally.
Okay.
So at this point, they're kind of separate.
All right. Thank you.
Question. I'm curious about Ludwig in terms of like how often you kind of find yourself like adding different types of layers and stuff like that. Like, is it really easy to keep up with the research that data scientists want at Uber?
So I'm actually not the right person to really answer that question. I can connect you with the person who created Ludwig, but I think, so yes, we definitely extend it and add more functionality. Really nice thing about Ludwig is because it's open source and its architecture is fairly straightforward, we actually see that people just come in and add features for us. And so it kind of becomes a centralized place where you just add new pieces of state of the art. So it may be that your problem is already can be solved by Ludwig, or it's maybe that it's easy to just add one piece, and then you can take benefit of the rest.
Sorry. So do you use Ludwig? Do you have like a good experience using it?
I have not used it myself.
I was curious because it's like if you define YAML, it's like when I do a deep learning model, I'll define a class and like different parts of it. And that way I have like class inheritance and I can extend it easily.
Yeah.
When you have YAML, you have to like make some sort of YAML override.
Oh yeah, right. In this case, you basically have to go to GitHub and add pull request to Ludwig to add more functionality. And then you would be able to use these kinds of features in Ludwig. So for example, if you look here, we have this encoder. So Ludwig uses encoder-decoder model. It's kind of a subset of deep learning architectures that you can do. You take your inputs, you encode them, you get feature vector, then you decode them into your result. And so you can, for example, define your new encoder, or you can have different input data type. But then you can use all the existing decoders that Ludwig have, or vice versa.
Thank you, Alex.
Thank you.